Hello everyone. So we already have uh, to some extent discussed the physics associated with sensors, and slowly we are moving towards the fabrication of sensors, or I would say different fabrication techniques that are associated with sensors. So today we will start the fabrication process, but before that just a quick recap of what we have done. Just I'm mentioning few physics that we have seen, for example thermal sensing, then capacitive sensing, then optical sensing, magnetic sensing. So the physics itself is very important while you design a sensor system. But in this case what we will do is we will slowly see how to fabricate those sensors as well. So in this case we first will see the techniques associated with microfabrication. Why we are interested in microfabrication? Because most of the sensors are in micron range, the dimensions. So you definitely need a microfabrication technique in order to fabricate those sensors. Apart from that, there are sensors which are made of or fabricated using different other techniques or various techniques that briefly we will discuss once we complete the microfabrication part. Microfabrication part is also important because this is sort of a standardized fabrication technique in most of the device fabrications. Now microfabrication can be divided broadly into 4 different processes. The first process associated with microfabrication is deposition. So from the name itself it is very clear that deposition is a technique in which you deposit certain material on top of a substrate. Usually while we fabricate electrodes of any device or sensors, we use deposition techniques. Now deposition techniques also can be of various types that we see as we progress. Then after deposition, the another very important process or technique in microfabrication is patterning. So patterning is a technique where you make different kind of patterns because it is needed. Different device has different geometries. For example, say if you want to make electrodes of a certain pattern, say the pattern of the electrode should be something like this, and that too in micron range. Then to fabricate these patterns, you have to have a patterning technique which will help us to fabricate this type of electrodes. So what you do is first you do the patterning and then you deposit material so that you get a electrode of your choice, or different, not only electrode, different other things associated with the device can be patterned. So this is a very important technique. Again, this is known as patterning. Then we have etching. Etching technique is a removal technique. If you want to remove certain material or certain, I would say, material that is not needed in the device any longer, so you need to remove those materials, you usually take help of etching technique. And finally we also have doping techniques. So doping techniques are mostly used in semiconductor device fabrications. So you also, I think you already know what is doping. Doping is to add impurity into a semiconductor or in any material for that matter. So when you dope, you usually target certain sort of properties. So you want to achieve certain sort of properties, that's why you dope a material with some other material so that you can achieve that electrical, mechanical, whatever property you target. So doping is also a very important process in microfabrication that we will see how we can dope a semiconductor or some material, what are the different techniques available for that. These are all microfabrication techniques, that is, these processes are needed in order to make a certain device. For example, say if you want to make an MOSFET, you need deposition, you need patterning, you need etching, and then you also will need doping. So these are major processes involved with microfabrication. Once you fabricate a device, you also need to characterize that. So that's why there are several characterization techniques are also available. So for example, if you want to characterize the morphology of a thin film, for example, you have deposited an electrode on top of a silicon substrate. Now you want to see whether this electrode is smooth enough, whether there is any crack, any defect present in the electrode or not. For that purpose, you need certain sort of imaging technique. So one of the very well known imaging technique is optical microscope. This is an optical imaging technique, but the limitation of optical microscope is you can't go below certain microns. So theoretically it can go say up to few hundred nanometers, but in practice you'll find if you want to check a feature size which is less than say 5 micron or certain cases less than say 1 micron, it's very difficult to actually image those features, because for that purpose you also need the object to be very close to the lens, which creates various problems, and there are theoretical limitations as well, which doesn't allow us to or do not allow us to image feature sizes that are very small. That's why we shifted to electron microscope. So in electron microscope what we do is, instead of optical signal, we send electrons, high energy electrons. So what is a light or optical signal? It's just photons. If I consider the particle equivalent of that, they are photons. So instead of photons, you send high energy electrons in order to image those techniques. So for that purpose, for imaging purpose, we have say FESEM, that is electron microscope. We have TEM, this is also an electron microscope, and then we have optical microscope that we know. Apart from that, we also have say AFM, which is atomic force microscope. That is again a different imaging technique altogether. We will see as we progress, we will see all these techniques in brief, what are those techniques are. So this is one type of characterization where we characterize the morphology of a certain say thin film or feature or certain device. Then we have material characterization. So material characterization is needed to confirm that whatever you have deposited is of a certain material that you desired or not. For example, or to check whether there is any contamination or not. For example, say you deposited gold on top of silicon. Now you want to ensure that the electrode that you have deposited is made of gold only, there is no contamination, so you will go for a material characterization. So as far as the material characterization is concerned, there are again various techniques, whereas various spectroscopic techniques, for example say UV visible spectroscopy, then you have Raman spectroscopy, so on and so forth. There are various other, FTIR is there, XRD is there. So there are various types of material characterization techniques available. Again in brief we will see maybe a few. However, we will mostly focus on the morphological characterization technique, because anyways material characterization technique is important, but that also, I mean, usually when you go for a sensor fabrication, you take a purest material. If you are synthesizing certain material, then again you have to go to this material characterization as well. We will discuss in brief that as well. So this is known as material characterization. Then we have electrical characterization, which is again very important, because most of the sensors that we will develop or we develop usually are electronic sensors. So you need the electronic output of that sensor. So for that purpose, there are various electronic characterization techniques. For example, you use digital multimeter, you use oscilloscope, you use vector network analyzer, so on and so forth. You use source meter, then there is probe station, there is parametric analyzer. So these electronic characterization techniques are also very important. So characterization is again a very vast field, but we will try to cover the important ones in this course. And as far as the microfabrication is concerned, we will cover deposition, patterning, etching and doping to see what are the different processes associated with that. Now, from the name itself, it is very clear that if it's a microfabrication technique, the feature size or the device size will be in the range of micron. And for that purpose, you need a very clean environment. For example, again, say you are developing a device where the electrode dimension is say the range of say 50 micron or say 5 micron. Now, if you do it in an ambient condition, for example, in this room, there are particles that are of very higher dimension compared to this. So what I mean by that, there are particles that has dimension of say 10 micron, 100 micron or even more in certain cases. Now, if you develop this device, say 5 micrometer device in this environment, there is a high chance that these particles from the air will get deposited on your device and the entire device will not work. For example, if you are developing this feature size of 5 micron and then if a big particle of say 50 micron sits on top of it, your device will not work. You can't even go for a deposition technique. So it's very important that you maintain a clean environment. So for that purpose, we use clean room. Now, clean room is a special environment where several parameters are controlled, monitored and maintained. So what are those parameters? So in a clean room, you will find we maintain temperature because it's again an important parameter as far as the device fabrication is concerned. We maintain humidity. We maintain the pressure inside that clean environment. We maintain contamination and we also maintain personal access. So clean rooms are a special arrangement where we try to maintain a certain sort of cleanliness, in short, and then we ensure that that cleanliness is maintained throughout. So how do we generate or how do we make a clean room? A schematic illustration is shown over here just to give you an idea that what a clean room is. For example, say if you want to make this room as a clean room or the room you are already or in a classroom, for example, say if you want to make a classroom or a laboratory, a clean room, what is needed is, so first thing that is required is you have to filter the air while the air is entering the room. So for that purpose, what they do is they use compressors. This compressor will suck in air from the environment and the air will go through different filters. So these are the filters, they are known as HEPA filter. So these filters restrict bigger size particles to enter into the room. So when this ambient air goes through these filters, the bigger size particles are stopped over here. Now this air will go inside the room and then they will go out again through a outlet and then this air will again go inside the room through this compressor. So it's like a circulation of air, but every time the air enters the room, the filters ensure that bigger size particles are not entering into the room. And second thing that is very important in this case is we maintain a laminar flow of air inside the room. So what is a laminar flow? Laminar flow is a flow that is in order. So it's like an fluid mechanic term. I am not going in details of that. So in short, if I say a laminar flow is where the velocity profiles are like this, there is no turbulence in the environment. So the problem with turbulence is if there is a turbulence, so a turbulent air usually creates an environment which is very dusty. For example, in this table or wherever you are sitting in that table, if there are different dust particle, and if the air that is flowing here is turbulent, very turbulent, then these dust particle will again come into the air circulation. So that is why laminar flow is preferred. So what they do is they send this laminar flow through the clean room, and then they maintain a certain sort of pressure inside the room. The purpose behind maintaining a pressure is, for example, if some person enters into the room and they will if they open the door while entering, if the pressure inside the room is high, so the airflow will be always from inside to outside. So outside air will not enter inside the clean room. I repeat, if the pressure inside the room is bit higher than outside, if somebody opens the door, then air will always flow from inside to outside, and outside air will not flow inside. So that will help to maintain the cleanliness, because outside air is not clean. If it enters the room, then anyways the room will get dirty or dusty, right? So that is why usually in microfabrication clean rooms they maintain a bit high pressure. And when people enter the clean room, they also need to go through certain protocols. So there are clean room suit which they need to wear. They go through an air shower. So before you enter the actual clean room, there are different other rooms that are there to ensure that the person that is accessing the clean room is clean enough to enter that room. So what they do is they put air shower from top, and when the person enters this room, then there will be a heavy air shower which ensures that if there is something, anyways the person has to wear a suit, clean room suit, that I will show you in an image. So once you wear the suit, so if there is anything on the suit, that will get washed away using that air shower, and then the person will enter the clean room for whatever process or whatever fabrication or whatever characterization he or she wants to do. So that is how the personal access is maintained. And then if you look at these tables that are used in clean room, they are there are different small holes on the table, on the surface of the table, so that the air that is coming from top, get a way to go below the table. Otherwise they will reflect from here, and there will be more turbulence on top of the table. Most of the devices you will keep on the table only. So if there is turbulence around, then there is a chance that even if there is some sort of dust that has deposited on the table, will again create certain issues. So that's why it's better if you can make an arrangement through which the air can pass through the table. So that's why they make small holes on the table or chairs in most of the furnitures. Okay, and based on the contamination present or based on the dust particle present in the clean room, one can also classify the clean room. So clean room contamination is measured. So airborne particles present within a cubic foot of air. So the contamination inside the clean room, I won't say it's a contamination, I will say the number of dust particles. So how they measure? They measure the number of dust particles present in a cubic foot of air inside the clean room, and based on that they determine the class of a clean room. So there are various classes. For example, if you want to make a device in nano domain or in submicron domain, you'll prefer an clean room which has less number of particles in each cubic foot of air. So your clean room standard should be higher, and that is how one should choose what clean room to be used. So there is a lot of arrangements needed in order to make a clean room. You can understand that there are a lot of things that one has to install and also monitor. It's not only installing, you have to also monitor that the clean room is properly functioning. Now if the clean room is not clean enough, the problem is your yield will be less. First thing, yield meaning, for example, you are making 100 devices, you'll see that only 10 devices are properly fabricated. Because the cleanliness is less, there are a lot of dust particles and other contamination that may come and sit on top of your device, and the device will stop functioning. And second thing is, if it's not clean at all, then you probably won't be able to make a device, because every time you make, there will be certain sort of dust particle contamination that will destroy your device. So that's why it's very important that you maintain the cleanliness inside a clean room, and you also know what is the standard of that clean room. So here I am showing the clean room standards. So previously the standard was known as 209E. According to that standard, the class of a clean room was decided based on the number of 0.5 micron sized or larger particle present in per cubic foot of air. So according to this standard, the reference was 0.5 micron sized particle. So the number of particle present in per cubic foot air, which has a dimension 0.5 micron or higher, will decide what is the class of this clean room. So accordingly, the standards are divided. So for example, say if you have a class 100 clean room, then in that clean room, if you take 1 cubic foot of air, the number of particle having size 0.5 micron or higher should be less than 100. Then we can call it class 100 clean room. So I mean, it should be between 100 and 10. If it is less than 10, then it's class 10 clean room. If it is less than 1, then it's class 1 clean room. So you can understand that how clean the air or environment should be, because the number of particle per cubic foot should be less than 100 and the particle size should be 0.5 micron or larger, right? So previously people used to use this standard in order to make different clean rooms, but as the technology advanced, people started working with very small sized particle, for example, very small sized channel length or devices in nanometer as well. So they have changed the standard to ISO 1464411 in this standard, because people understood that it's not only 0.5 micron or less, even 0.1 micron also can create different issues if your device dimension is very small. So they started also considering 100 nanometer or 0.1 micron sized particles as well while they are developing the clean rooms. And according to that, they have divided the clean rooms into 9 different standards, ISO 1 to ISO 9, where ISO 9 is the ambient room air. So if you see that ISO 9 standard, 0.5 micron or higher particle numbers are around 3.5 crore. This is a standard room air. So the number of particles per cubic foot that has a size of 0.5 micron or high is 3.5 crore. And then you want to reduce that number to say 3 or 35 in ISO 2 or ISO 3. So this is the level of cleanliness one can expect or one need to fabricate different devices. So one needs this type of cleanliness inside the clean room to fabricate different sort of different kinds of devices. Now here a comparison also given, 209 standard, 209E standard and ISO standard. So say class 100 is equivalent to ISO 5, and there you also consider 0.1 micron sized particle or less. So this particular information is given over here to give you an idea that how important the cleanliness is and how people differentiate different clean rooms. So if you go to industry grade clean room, you may also find ISO 1 clean rooms, because in industry grade clean rooms they produce lot of devices and the yield has to be very, very high. However, in case of research laboratories, you may compromise the cleanliness a bit, because even if the yield is bit less, it's okay, because you are not fabricating say a large number of devices. In research, you fabricate a few devices and do research and see whether it is working or not. However, it is expected that the cleanliness of a clean room is much higher. and the investment associated with a clean room is also very high. So it's not very easy to create a clean room setup. It may take say crores of investment, 100 crores, 200 crores, say 500, 600 crores is something which I think is the investment that is required in order to create a full-fledged clean room with all the equipments and all. So it's not a very affordable kind of setup. So one has to invest a lot in order to create a clean room, and that's why it's very important that you maintain that clean room properly. Otherwise, if you are unable to maintain the cleanliness inside a clean room, then the entire purpose will not be served. Okay. So just for your reference, I have given some of the images of different section of a clean room. For example, say this is a section of a clean room inside a clean room, and this is another section of a clean room where the lights are yellow. Oftentimes we call it a yellow room as well. So why the lights are yellow? Because here we use say photosensitive materials, photoresistant, etc. Because the materials are very sensitive to the light, so it's better we also control the light inside the room. So that's why we use yellow lights inside that room. And then there are device or different instruments are kept. You can see these are fume hoods, and then people are working inside that clean room, and this is the typical clean room suit. Okay, so that is how it looks. So one has to wear gloves and cover from top to toe while they are entering the clean room, just to make sure that if there is any dust particle present in his clothes and etc., that doesn't contaminate the entire clean room setup. So you have to wear everything over the clothes that you are wearing, and then you have to go through an air shower just to ensure if there is something in this suit that washes away before you enter. So, and this is for example an image of a FESM. This is how it looks. I have taken this. Most of the images are taken from different sources. Okay, and this is how it looks. The instrument looks. To maintain the instruments also it's very difficult, because you can see that there are different parts of this instrument, and one has to take care of all these things in order to maintain the entire system. There are different gas lines present over here, so you also need to check the concentration of different gases inside a clean room to ensure the safety. So safety is again a very important concern that one is to address. Then for example, it also needs liquid nitrogen. So there are liquid nitrogen cabinets, and then these liquid nitrogens will be kept somewhere inside the room, inside a container. So one has to make sure that these are properly kept. So it's not an very easy job. One has to go through a training in order to just learn the clean room practices. Okay, so this is how it looks, and this is also needed for microfabrications. Okay, so from this lecture what we understood is clean room is required for almost all microfabrication techniques. Why it is needed I already told. The yield is very important. So if you don't, or in certain cases you can't even fabricate a device without a clean room setup, because the dust particle size is much higher than the feature size that you are using inside a device. Or even if it is higher, because if it's not clean, then different things will get deposited, your device will not perform properly. Then clean rooms are of different grades and standards. We also have seen the grades and standards associated with the clean room. Then microfabrication facilities and clean room setup are usually expensive. I also have mentioned it's not a very low cost setup. One has to spend a lot of money in order to create a clean room setup, and that's why maintaining that setup is also very expensive. Okay, so in the upcoming discussion we will discuss different deposition techniques. What are the deposition techniques associated with device fabrication? Till then, thank you.